11.2. So now we're going to move past the idea of graphing. We're going to go into different ways that we can algebraically determine what a limit is. So we've got some different techniques that we're going to be doing. The first one, and I'm just going to follow along with your notes, the first one that we're going to be doing is just direct substitution, which we will always try first, because if it works out, great. If it doesn't, well, then we'll come up with another way to do something. So if I take a look at this, can I evaluate where cosine of pi is? Yes. Yes, I can. Well, as soon as you plug in the limit, you actually substitute it in, the limit notation, this LIM business, needs to disappear. So we're going to do cosine of, now plug in the x value, which is going to be pi. Well, we all know what cosine of pi is. Cosine of pi is -1. Therefore, the limit as x approaches pi of cosine of x is equal to -1. And that is what the graph is going to do, but there's no need to look at it. We can actually just plug it in and see what happens. Let's take a look at this one. I see a polynomial, which I know I can plug numbers into. I'm just going to go ahead and plug the 5 in and see what happens. Remember, as soon as you plug the 5 in, you drop the notation. So all of the x's are going to be replaced with 5s now. And then just do the math. The only time we get worried about this is if we get something that we can't really calculate. So maybe we get a 0 over a 0. That's pretty bad. But I'm going to show you how to deal with that. Or some other number over 0. And we've got a problem with that. And that's probably when we're going to grab our calculator. All right, so if we plug this in, and we just do the math to clean this thing up, it looks like we're going to get -8. Comes out to be a nice pretty number. That means that the limit as x approaches 5 of the polynomial is going to be -8. All right, moving on to the next slide. Same idea here. So the first thing I'm always going to try is direct substitution. So if I do direct substitution, so just plug in what I know, I'm going to get -3 squared plus -3 minus 6 all over -3 plus 3. All right, I'm worried about the denominator because I see 0, and that's not good. But if this ends up being 0 over 0, I know how to handle this. All right, so I'm going to get 9 minus 3 minus 6 on the top. That's 0 over 0. This is indeterminate form. Whenever you get 0 over 0, it's basically telling you there's something else that you could have done. There's something that you could have canceled or eliminated top and bottom to get rid of this whole 0 over 0 business. So we're going to go back to the beginning and we're going to factor. So this is called dividing out or factoring technique. Now, I'm not actually going to be plugging in the value, so I have to keep my limit notation this time. All right, so now if I factor the top, I think I get an x plus 3 and an x minus 2. All over the x plus 3 that was already there. All right, here's why we got the 0 over 0. If you take a look at this, this x plus 3 factor matches top and bottom. If you plug the -3's in right now, you get a 0 on the top for the first factor and a 0 on the bottom. That's the 0 over 0 that indeterminate form was trying to tell us about. So let's just get rid of it. So it's called dividing out technique because we're dividing it out. All right, so now if we have the limit, still not plugging this -3 in yet, so I'm going to carry my notation with me, of x minus 2. This looks a whole heck of a lot better. Now let's actually plug the -3 in. So that's going to be -3 minus 2. That gives me -5, which means my original problem is going to have a limit of -5. All right, why don't you try this one on number 8? I'm going to go ahead and pause, and I'll solve the problem. But just take a minute, see if you can plug in. Always try plugging in the limit value first. Try direct substitution. You never know. It may actually work from the beginning. You don't want to waste extra time doing something else. So go ahead and plug it in. If it doesn't work, try another technique, and then check back. Okay, so I tried direct substitution. I get 0 over 0 indeterminate form. But I know that I don't have to grab my calculator because I think this is something that I can factor out. So I factored it. They're the x plus 1s that were knocking each other out. Get rid of them. Now, after I've gotten rid of them, notice I kept my limit notation with me until I actually plugged the -1 back in. And it looks like I get -5. So really, your first course of action, I would hope, would be to try direct substitution. Hands down the easiest one to do. If it doesn't work, well, of course, then you have to come up with something else to do. Like this. So if I do my direct substitution right now on number 9 and I plug my zeros in, I'm going to get 1 minus 1 over 0. This is not going to work. Now, when you're doing direct substitution, do you have to show me that you're doing it to check and see if it's going to work or not? No, not at all. You don't. You can go ahead and mentally try direct substitution, and if it doesn't work, don't waste your lead on it, and sure, don't waste your eraser on it. So what we're going to do with this is a little bit different than what we've done in the past. Notice that we have a radical in the question, but the radical itself is actually in the numerator. We are still going to rationalize like we normally would when we had fractions, when we had radical in the bottom, except this time we're going to rationalize the numerator. So what I'm going to do is I'm going to multiply top and bottom by the conjugate of the numerator. So again, when we do these problems, you rationalize the top, not the bottom. All right, now we actually haven't plugged in the limit yet, so let's go ahead and keep that with us. And yes, you definitely want to multiply out the top, but it's really not too bad because it's a difference of squares. It's a beautiful part about conjugates. So the first ones are going to give us x plus 1 when we multiply. The outer and the inner are going to cancel, and then we just get minus 1 from the last. Do not distribute the bottom. It just gives you extra work that you're going to have to factor out again later. So let's just keep it in factored form. All right. So now remember the idea of having 0 over 0 means that there was something there that could have been canceled. All right, so if we keep cleaning this up, I'm going to get an x on the top and that big huge mess on the bottom. But there are the values that were actually knocking each other out when we plugged in the 0. It's the x right there and the x right there. So let's go ahead and cancel those guys out and just get rid of them. Remember, whenever you cancel everything out from the top of a fraction, you still have to have something up there. So remember, it's going to be a 1, unless you have another number or another variable. Let's go ahead and bring down what we have. Now let's try direct substitution. So I think this is going to work now. Which I believe gives us 1/2. So way back up at the beginning here, I wrote stuff at the end of it. Let's go ahead and write it back the original way. So the limit, as x approaches 0, of that mess that we had in the beginning is actually going to be 1/2. All right. Example number 10 is kind of like example number 9, but in that you need to clean stuff up. Not that you're going to rationalize, just that you're going to clean stuff up. So if we take a look at this, I want you to treat it just like you would any of the other problems that we've done this year. You have fractions and fractions, which is unpleasant. So let's clean it up. Remember that this is still just a lot of algebra. So I'm not a big fan of fractions and fractions, you guys know that. So what I'm going to do is I'm going to figure out what the common denominator would be, or actually let's just get a common denominator and make it easy on ourselves. So I'm going to keep my limit notation because I'm not actually going to do anything with it yet. The first fraction is going to need a 4 top and bottom because the second fraction has it. The first fraction is going to need a 4 minus x because the first fraction has it, but it does not. And then the bottom, well, the bottom is x over 1. So with x over 1, I need the 4, and I need the 4 minus x. I need both of them. Okay, by going through and getting all of the denominators to match, you know we can actually just get rid of these guys now, which is kind of nice. All right, so we've got the limit as x approaches 0 of 4 minus the quantity of 4 minus x. Notice I'm using parentheses here. If I wasn't using parentheses, I'd probably be in trouble. Just with that whole negative business. Don't distribute out the bottom again. All right, so I've got my limit as x approaches 0. Clean up the top. 4's cancel. Actually, that x becomes positive now. It's kind of nice. Now, I did kind of jump past the whole direct substitution because I went through and mentally checked it and knew it wasn't going to work. And I'm hoping that you did the same thing because there are the culprits right there. That x over x is going to give us the 0 over 0. So let's get rid of those guys now. So that's going to give me, still haven't plugged in the limit yet or evaluated it. You have to have something on the top, so keep that 1 there. Now let's plug in the 0, and I think this is going to work out nicely. And that gives us, looks like 1/16. So then, and I already wrote next to the original question, so let's just go back and wrote down what we had in the beginning. So the limit as x approaches 0 of that terrible looking mess, which we cleaned up nicely. Got a little ugly at first, but cleaned up pretty good. Ends up being 1/16. So we just have a couple of different techniques for you to be able to evaluate limits. All right, so now we're the same idea here. Now this is a problem just like what you did before, but we're talking about one-sided limits now. So this first question, number 11, is coming in from the left only. So I don't really care what's happening on the right-hand side. So these are one-sided limits where the limit, so this little exponent here tells us exactly what we're supposed to be looking at. So this right here tells me that I'm coming in from the left. So from the left. All right. So we graphed something like this. So why don't you go ahead and take a minute. And you can either make a table or you can actually create the graph. I think I'm just going to make a table real quick. So let's pause and see if you and I match. Okay, so I just picked values to the left of 0, started at -2 and just kept cutting my distance in half. It's like the idea of trying to find out what the fractions are doing too. Now I know when I plug in 0, it's not going to work, which I just wrote the no there. I also know that because of the nature of these absolute values divided by just a plain old x, that I'm going to see a jump in my graph. So all I really care about is what does it look like it's getting close to. Well, take a look at my y's. I know that if I keep plugging in negative numbers that are closer and closer and closer and closer and closer to 0, I'm just going to keep getting -2. So way back up here, let's squeeze our little equal sign in there. It's going to be -2. Now it's not going to get there, which is okay. Remember, it's about the approach. Why don't you try number 12, and then we'll compare answers. So this time, based off of the notation, I see that little plus sign as the exponent on the 2. So that means that I am coming in from the right only. I don't really care about the left. So from the right. So when I made my table, I chose values that were to the right of 0. Yeah, I plugged in 0 just to have, kind of a guide. I know it's not going to work anyway, but then I plug in stuff to the right of that. And it looks like I'm going to keep getting 2s. And I know based off of the pattern that if I keep plugging in stuff that's closer and closer and closer and closer to that 0, but still on the positive side, I'm going to keep getting 2. All right. Now is when things start really getting interesting. So one of the first things that we had talked to you guys about this year was difference quotient, which you'll notice is in your notes. The difference quotient talks specifically about just f of x plus h minus f of x all over h. We're going to start throwing limits in front of it and seeing what happens. So in this section, all we're going to do is just plug stuff in and see what happens. That's it. So it's the exact same thing that you did first semester. You just want to make sure that you're following the directions. So on this one, I'm going to do the limit as h approaches 0. All right, so I'm going to keep that notation until I actually plug in the 0. In this one, it looks like f of 3 plus h. So we're going to go back to the original function, and everywhere I see an x, I'm going to plug in 3 plus h this time. And then I'm going to subtract f of 3. All right, so I'll go back to the original, and I'll plug 3 in for all of my x's. And that's going to be all over h. All right, so now we just have some algebra that we need to clean up. Remember to keep that notation with you as long as, well, up until the point where you actually plug it in. All right, so if we clean this up, nope, that is not a 3. Let's back up. Again, just doing the math. Remember, whenever you're doing something that looks like this, everything without the h's should go away. So the 9's are gone, the 1's are gone. Okay, this is good. Now, once you get to the point where it looks like it's cleaned up a little bit, go ahead and take a stab at direct substitution. However, really shouldn't take you too long to see that this is not going to work, because you've got everything on the top has an h times by it, so that becomes 0, and then you have the h in the bottom, which is 0. All right, so let's try the techniques that we know. Let's factor out. That is not a squared. I'm not sure why I put that there. All right, the h's cancel. There we go. There was the culprit. So let's eliminate those guys. And then we can do, still haven't plugged in the 0, limit as h approaches 0, of 6 plus h. Now plug in the 0. We just get 6 plus 0, which is 6. So way back up here, the limit as h approaches 0 of this business, way down at the end, we can say it's just 6. Okay? So a little bit more practice on stuff that we did first semester, kind of difference quotient-esque. So let's take a look at the next slide. And it's a lot like what actually it is the difference quotient. So why don't you take a minute, and I'm going to go ahead and fill in the first, unpause it, and then we'll check, and then I'll keep pausing and we'll see how it goes. Okay, so my first step, I'm just plugging it in. Again, just like the difference quotient. Do the exact same things you normally would. The only difference now is we're throwing a limit in front of it, which you don't really deal with until the very end. So let's go ahead and go on to the next step. Okay, so now everything is distributed. At this point, everything without h's should cancel. And if it doesn't, we made a mistake somewhere. But looks pretty good. Now, keep in mind what you've been doing first semester. When we got down to this point, we factored out h. So, factor out h. Now if you try to plug in, we get that 0 over 0 business right there with those h's, so let's get rid of those guys. Now, go ahead and plug in the 0. Remember, you're plugging in 0 for the h, since that's what's on the bottom of the limit. So it looks like we end up with 2x plus 4. So way back up here, let's go ahead and set this thing equal to 2x plus 4. So difference quotient, just throwing a limit in front of it. All right, last one. So same idea. Go ahead and plug it in. We'll pause, see if we match, and then I think we're going to have to use some of the tools that we've learned recently. All right, so it's all plugged in. If I plug in my 0 right now for my h, I definitely get 0 over 0, which again, I'm always checking, because it could happen that you don't have to keep going. You just plug the 0 in and you're good. All right, but this looks like something new. So I see radicals. We're going to rationalize the top. Remember, we don't rationalize the bottom here. We rationalize the top. So multiply by the conjugate, top and bottom. Remember, the conjugate is you change the sign between the two terms. Don't change the sign inside the radical. That doesn't do you any good. Actually, it just makes more work for you. It doesn't work at all. All right, so the beautiful part is when we multiply out the top, we get a difference of squares. So the first two guys multiplied together, you just drop the roots because they match. Same thing with the last ones. They match. Don't multiply out the bottom. It just requires more work for you to do in the future, so we're just going to avoid that at all costs. All right, so now we've rationalized the top. Go ahead and cancel out those x's that I see there. It also looks like I'm now going to have h's that cancel. So that 0 over 0 that I got originally, there's the culprit right there, those h's that match. So let's get rid of those. And then now, still haven't plugged in the 0, so keep the notation with you until you actually do it. Now, let's plug them in. So once we plug the 0 in, I just get root x because the h just disappears in root x. And just remember what you know. Those guys match. So if you have a root x plus a root x, you have a total of 2 root x's. And we can leave it that way for now. We'll play with it later. So it's going to be 1 over 2 root x. All right, so there we go. I think that covers it for this section.